in this video we're going to go ahead and do some practice using the central limit theorem to find probabilities. A good clue that this is a question that involves the central limit theorem is you are asked about the probability of a mean instead of the probability of an individual, or if you're given a sample size. Either one of those is usually a good clue that we're working with the central limit theorem. And in that case, you're working with a sampling distribution. So the mean of your distribution should be the mean of the population, should be given in the problem. The standard deviation of your sampling distribution is going to be the given standard deviation of your population divided by the square root of your sample size. Everything else about probability problems is going to work exactly like the previous examples we've done. Let's go ahead and take a look at some and get some practice. So this first example says the average number of earthquakes that occurs in Los Angeles over 1 month is 36. Assume the population standard deviation is 3.6. If a random sample of 35 months is selected, find the probability that the mean of the sample is between 34 and 37.5. So, I am given the average number of earthquakes for LA over 1 month, so I know the mean of the population is 36. I'm told the population standard deviation is 3.6. I'm told I'm collecting a random sample of 35 months. And then I want the probability that the mean of the sample is between these values. So I want the probability that the mean is between 34 and 37.5. And notice I'm using the symbol for mean instead of just an X for a data value. That means on my graph, I'm not plotting X, I'm plotting X bar. My mean is still 36, but now my modified standard deviation is going to be 3.6 divided by the square root of 35. And I'm going to do that calculation really quick. I get 0.6085. I'm going to round that to 0.61. And so I'm going to label my picture over here. So we're going to get 36.61, and then 36.61 plus 0.61 is going to give me 37.22 and 37.83. And then I'm going to do the same thing in the other direction. So 36 minus 0.61. 34.78 and 34.17. Now I'm going to go ahead and I'm going to mark. So I want 34, which I know is going to be off the chart here, and then 37.5, which is going to be between 0.22 and 0.83, which is right here. I want this area here, and I already see it's most of the curve, so I'm expecting that this answer is going to be probably like 95% or more. I'm expecting a big answer. I'm going to go ahead and do this on the TI-84. So I'm going to do normal CDF, lower bound, upper bound, mean, standard deviation. So my lower bound is 34, my upper bound is 37.5, my mean is 36, and then for my standard deviation, I'm going to enter the formula 3.6 divided by the square root of 35, so I get a nice precise answer. So second bar is option 2. and we get 0.9926, which makes absolute sense given how much of the curve we shaded. We shaded almost all of it except that little itty bitty bit out there. Let's go ahead and try another one. So this next one says per capita income for California for 2025 was $91,116 with a standard deviation of 29,000. What is the probability that a random sample of 34 California residents has a mean income greater than 90,000? So I know my population mean is 91,116. I know the standard deviation for the population is 29,000. I know my sample size is 34. And I know that I'm asking a probability question for the sample mean to be greater than 90,000. So I'm going to do what I did last time. I'm going to do that quick standard deviation for my sampling distribution, which is population value divided by square root of sample size. And we get 497. And I'm going to round that down to just 3. Just for the purposes of labeling, I already know when I put it in my calculator, I'm going to put the exact. For the purposes of labeling, our mean, 91,116. And then to that 91,116, I'm going to add 4,973. I'm going to go ahead and pause this. You have to watch me do it, but that is how I'm labeling that whole curve. Alright, so I've got my axis labeled with my standard deviation. And I'm going to go ahead and mark my area of interest. So I want greater than 90,000. 90,000 is just a little bit below the mean, but within 1 standard deviation. And I want greater than, so I want this side of the curve, and I can already tell by looking it's going to be just a little bit bigger than 50% or 0.5. But let's go ahead and set up our normal function call. So normal CDF, lower bound, upper bound, mean, standard deviation. Our lower bound is the 90,000. And my upper bound is that positive infinity 1e 99. Mean of 91,116. Standard deviation of 29,000 divided by the square root of 34. Get 0.5888 rounded, which is just a little bit bigger than 50%, which makes sense because we know this is our 50% marker, and we're just a little bit above that. All right, if you have any questions on those 2 examples, feel free to send me an email. Otherwise, I will see you in our next video.